Good afternoon. Thank you very much for joining this very exciting first for this academic year and first online, actually, I think, Royal Statistical Society Social Statistics discussion section, which is on data linkage methods and quality, quite appropriate for the times we live in. My name is Andromachi Celloni. I'm a professor of quantitative criminology at Nottingham Trent University. And since I think a day before the lockdown, I joined the Ministry of Justice as academic lead for the Data First program. And I'll tell a little bit about it in a bit. But first, I'd like to thank the organizers of this online seminar because I don't want to get all the glory. Actually, I came in quite late. So originally, this was envisaged as a seminar that would actually follow quite nicely from the Off-Trans Statistics published back in August, documentation of the future of data linking methods. And for some time, Carl Ashworth, another member of the Social Statistics Executive Committee, RSS section, and Hannah Fissenbach from ONS were trying to organize. Then Hannah moved on to better places, I hope. And then the bulk of the organizing eventually was supported by the ONS colleagues Claire Shenton and Charlie Roth-Smith. So thank you very much. And obviously, Tricia Dodd is the seminars organizer from the Social Statistics Committee. So with thanks to them, we're going to have a set of really exciting talks at the moment. But if you allow me to introduce a bit the Data First MOJ ADR program. ADR starts from Administrative Data Research UK, and it is funded by the ESSC. So in collaboration with the Ministry of Justice, they have set up this ambitious Data First program, and we're hopefully going to hear a bit more from the first presenter, Robin Lineker, who has done most of, who has actually led the data linking. So this program aims to de-identify administrative data that come to the Ministry of Justice, either through the HMCTS, which has magistrate courts and tribunals system, or the HMPPS, which is prisons and probation. And so far, the MOJ team has succeeded to do so with the Magistrates Court and the Crown Court data. And they have also produced a linking data set where you can link, say, the same case or the same defendant within each court, each set of courts, or across them. These are already submitted to the Off-Trans Statistics, the Secure Research Service, and can be used by accredited researchers for approved projects, when, of course, these researchers also belong to an assured, to an institution with assured organizational connectivity. There is a future. Oh, can you hear me right? Because I can hear myself now. Sorry. Is that okay? Yeah. There's the Data First project is very ambitious, so it hopes to link cases not just for the criminal courts, but the family courts and the civil justice, but also link MOJ data to other government departments. And so far, there's successful linking between magistrates and data and the Department for Education data. So without further ado, oh yeah, I should also mention that there's going to be, for people who might be interested, there should be a set of research fellowships coming from the ESSC to use this really rich set of data that are publicly available first time ever. The first one has the deadline just ended on the 20th of October, but there are going to be more coming up. So please, look out for them. Before introducing the speakers, some housekeeping things now with the online seminars. If you could please keep your videos and mics off, and if you'd like to ask a question presenter, just feel free to type it in the message board, or if you want to ask it yourself, just raise your hand. So without further ado, I'll introduce the first speaker, Robin Lineker from MOJ.
Hi, everybody. Thanks very much for the introduction, Mackie. You've saved me a bit of time in introducing the Data First work. So I work as part of this Data First program. My name is Robin Lineker, and I work on a new team who are modernising our approach to record linkage at the Ministry of Justice. The work I'm going to talk about today was done by myself, but also two of my colleagues, Sam Lindsay and Theodore Manassas. So we do the kind of data linking methodology. So the talk today is going to focus on our probabilistic record linkage software, which is called Splink. And this is a free and open source tool that we've developed to tackle some of the big record linkage problems that we have at the MOJ. It estimates the Foleggi-Sunter model, but it introduces a number of innovations that help us improve the accuracy of the model. And it also allows us to estimate the model on very large data sets. So nothing today really I'm going to talk about is MOJ data specific, and with just a few lines of code, you can actually use this software yourself to tackle your own record linkage problems. So a very quick overview of the talk. I'll motivate the talk by introducing the business problem that we're trying to solve with record linkage. I'll then talk a bit about why we decided to write some new data linking software. I'll talk a bit about what the software does and give you a bit of a flavor of how it works. I'll talk about some of the innovative features of the software that help increase linkage accuracy, and then I'll just move on to a few conclusions. So why are we working on record linkage at the MOJ? So we have many different large-scale sources of administrative data from prisons, from probation, from courts, family and civil, and there are no unique identifiers which appear in all of these systems. So what that means is that we have to use personal identifiers to link together the data, which is to say we're mostly using things like people's names, dates of birth, and that sort of thing to work out if they're the same person. Before we share that data any further, it's then anonymized, so we don't share those personal identifiers, but we do use them for linking. So why do we care about doing data linking? Well, it's really just got the potential to give us a much richer picture of the justice system. So it helps us better understand journeys through the system as people go from the court system through to the prison system and so on. And that can really help us understand the effectiveness of interventions and also repeat users of justice services. So moving on to the technical challenges, really the biggest technical challenge we have with record linkage is that we've got tens of millions of records across multiple different computer systems with varying degrees of data quality. And those data sources typically need to be both linked and deduplicated. And so, and also with this really wide variety of input data sets, we want a consistent approach to data linking. So we need a really flexible solution that can accommodate all of these different types of data. So as a new team, about a year ago, we were all fairly new to record linkage, and we needed to decide on an approach. So we started with a literature review, and we started with desk research into data linking theory and practice. And we found that one of the most common theoretical approaches described in the literature is the Foleggi-Sunter model. This is a statistical model. It's got a long history of application for high profile and high impact record linkage tasks. So it's used at the US Census Bureau and at the UK Office for National Statistics. And we found that a really key benefit of this model is explainability. So the model uses a number of parameters, each of which has quite an intuitive explanation that can be understood even by a non-technical audience. And the relative kind of simplicity of the model also means that it's easier to understand and explain how biases and linkage may occur, such as maybe varying levels of accuracy for different ethnic groups. And this transparency is really important for us because it helps us mitigate many of the concerns that people have around machine learning and sort of black box algorithms. There are certainly more sophisticated models out there in the recent literature on record linkage, which would probably have a bit higher accuracy, but I do think that that often comes at the expense of higher complexity, lower explainability, and often longer processing times on big data sets. And in addition, we sort of judge that the potential for improvement in accuracy over the Foleggi-Sunter approach is probably relatively modest. So after settling on the Linkage Center approach, we started to review the available free and open source software that we could use to estimate the model, and we concentrated on packages which are available in R, Python, and Apache Spark, because these are the tools which are available on our analytical platform. And we found that a package which is written in R called FastLink. We found that it performs comparatively well. It's rigorous. There's a formal academic paper that supports its methodology. So it's really good, but the problem is it doesn't scale very well. So the FastLink paper's got this useful chart, which is at the bottom right of this slide. And that shows how runtimes change as the dataset size increases. And we see that as we approach 300,000 input records on the chart here, it's comparing various different libraries. FastLink is the fastest, but you're still going on for 10 hours of runtime, even parallelized for 300,000 records. So when we're sort of talking about the sort of 10 million plus records that we have, the runtimes, well, it probably would never complete. So we kind of read the paper and we looked at the code, and what we found is the code and the way that you can estimate the model is actually really well suited to parallelization. And this makes it a really good fit for parallelized computation frameworks like Apache Spark, which send different tasks off to a cluster of computers. So we sort of concluded that there's really good record linkage software out there, but it just wasn't fast enough to use at the scale of data we have. And that's why we set out to develop this new software package that would underpin all of the data linking work that we've been doing. This is the software package called Splink, and that's now available for you to all download and use. So thinking about the aims of the software that we've developed, it's to work at this much greater scale. So we're targeting being able to link and deduplicate 100 million records plus. It will give you results faster than other open source implementations. So we're looking at runtimes of less than an hour, even for some of these really big record linkage tasks. It's got a very transparent methodology, so the match scores can be explained both graphically and in words, and it's got accuracy, which is similar to some of the best alternatives, whether those are open source or commercial packages. One of the things that the software does is it gives linked data users access to link confidence, so they can perform sensitivity analysis. And we've deliberately built in considerable flexibility and customizability to enable it to tackle the majority of record linkage and deduplication problems. And finally, we've tried to make the software really, really robust. So there's an automated suite of quality assurance tests that every time we update the code, it checks that it's still kind of giving you the right answer and estimating the model correctly. So I don't have time for a demo today, but I did want to mention that you can actually try the software yourself in the browser using the link on this slide, which is at the bottom of every slide. So if you go to that link, there's this little button which says Launch Binder, and if you click on that, it'll open Jupyter Notebook in your web browser, so you can actually try the software out without having to install anything. So what I'm going to do today is I'm just going to give you a really quick flavor of what the software looks like rather than doing a demo. So imagine we've got some data that looks like this, and maybe we want to deduplicate it. So we've got first name, surname, date of birth, city, and email. And we can already see in just the top 5 rows that we've got a lot of deduplication, we've got transcription errors and that sort of thing. And the task that we really want to do is work out which of these people are the same person. When we use the software, the first thing we have to do is just basically tell it what to do. So give it some settings, and I won't go through this in detail, but basically here we're telling the software that we're doing a dedupe only rather than a linking task. We give it some blocking rules, which tell it how to create pairwise record comparisons. And then we tell it which columns are relevant to comparison. So we want it to compare, when we're doing pairwise record comparisons, first name, surname, date of birth, city, and email. And this is also where we can configure some aspects of those comparisons. So for here, for instance, we're doing term frequency adjustments on the name columns. So what that'll do is it allow there to be different estimates for, let's say, the first name John, which is quite common, relative to the first name Robin, which is relatively uncommon. Once we've set up the problem, you then just run the 3 lines of code which are on this slide. And what that does is it will run the expectation maximization algorithm to estimate the model parameters, and then it will output a data set of scored pairwise record comparisons. So the table at the bottom of this slide is just a couple of rows of sort of what the output looks like. So all of the data I'm showing you today is just fake data we made up, by the way. So for each pair of records, Splink will estimate whether these 2 records are a match, and it will give an estimate of match confidence. So another output you often want here is clusters. So that's whole groups of records which Splink estimates are the same person rather than just these pairwise comparisons. And if you have a look at the online demo, there's some code on there that shows you how to do that. So I mentioned the algorithm is very transparent and it outputs quite a few diagnostics to tell you what's going on. So I just wanted to run through a few examples on this. So these are some automatic charts which are produced when you run the software. The one on the left is telling you about the distribution of comparisons. So if we look at the city chart, which is the one at the top left, that's telling us that there's a good mix of values where the city matches and doesn't match. And down at the bottom on the surname one, that's telling you that there's quite a lot of records where the surname matches. There's relatively few records where the surname fuzzy matches. So that's where it almost matches, but not quite. And then there's also quite a lot of records where the surname doesn't match. So that tells you a bit about your data. Then on the right-hand side, we've got a chart which essentially is a way of representing the parameter estimates of the Lineage model. And it basically tells you how much the match probability is pulled up or pulled down depending on different situations. So if we look at the city one, you can imagine that a match on city is kind of interesting information, but it's not really a clincher because if two people are in London, doesn't mean they're the same person. So that's kind of telling us that a match on city will pull the probability up a bit, but not that much. And similarly, a non-match on city, maybe there are typos in that or people represent their cities differently. Again, it doesn't pull the probability of a match down too much. If we look at something like the email one, we can start to get a bit of an intuition for this. So two people very rarely will have exactly the same email address, probably almost never, and certainly in this data set. So if you get an exact match on the email, we can see that that's really pulling the probability of a match up really strongly. But it's saying that a non-match on email doesn't pull the probability down quite so much because some people have two emails or maybe there's a typo in it. So here's a couple more slides. So those first two were sort of just telling you a bit about the data and the parameter estimates. The other thing we're really interested in with the Lineage Center model and the expectation maximization algorithm is basically convergence. So there's no guarantee in the expectation maximization approach that you hit a global optimum. And so it's usually interesting to see how the iteration occurred. And these two charts are showing you that. So lambda is the overall proportion of matches which are being estimated. And down here is just one of these charts for date of birth. So if you sort of see anything funny going on in those charts, you can get a bit of a sense that perhaps you're not iterating towards a global maximum. The other thing about transparency that we quite like is this thing called an intuition report. So I'm not going to read through this in any depth, but the idea is that for any two input records, so here at the top right, we've got these two people called Isabella, probably Cooper, but maybe there's a typo there. We can ask Splink how it computed the match score. And what it will do is it'll sort of say, we started with a sort of Bayesian prior of X, and then we looked at the first name and saw it matched, and we updated that prior with information from the parameters of the Lineage Center model. So we've now got an updated belief, and we can do that iteratively. So we do first name, surname, and so on until we get our final estimate of match probability. And so for any pairwise record comparison, we can produce this report, which really helps to understand exactly what the model's doing. So I just wanted to mention a few of the innovations around accuracy to finish up here. There's some sort of new things that this software does that maybe are hard to do in other packages. So let's think about the task of deduplicating a large list of people, and suppose we have address data for those people. So that'll typically be a one-to-many relationship in that one person has many addresses because they move. One of the things that the software allows you to do is array comparisons. So to link people based on that address data, you often need to ask questions like, well, they've got many addresses, but does at least one address match? Or even does at least one address fuzzy match? And speaking of addresses, another interesting thing is around data vintages. So if the address, the observation of the address was made just days apart, probably quite likely the person has moved, so that's probably evidence against it being the same person. But if you're comparing two observations which were made years apart, that's quite different. And people move within the space of a few years. And so the effect that it has on the probability of a match is different. And this is something that can be explicitly modeled in the software. Also, if you have things like postcodes, you can map this to geographic location. And you might want to compare your records based on geographical distance rather than looking at like distances in the strings of the postcodes themselves. So when people move, they tend to move fairly close to home, and they rarely move hundreds of miles away. So that's again something that you can use. And of course, these sort of concepts, they're useful to many data types and not just addresses. Another thing that you can model is name inversions. So sometimes people will accidentally put a person's first name in the surname column and vice versa. Again, in Splink, we're able to allow the Verlegi Center model to estimate a separate parameter for this name inversion situation. Another piece of useful functionality is the variety of string comparison functions that we provide from the literature. So we've got native Scala implementations of a bunch of different functions like demetaphone and Winkler, which makes them really fast. Finally, collaboration. So I'll just run through this very quickly. So first of all, we're really indebted to ONS here, in particular Rachel Shipsey's team. So she's actually going to be presenting in a bit, I think. So thank you to her for all their insights. They've given us methodological advice, and they've also helped with the QA on this work. The other thing to say around collaboration is Splink is 100% open source, so please just do have a go with it. Tell us about problems with it using GitHub or email me. And we'd actually really love people just to get involved with this. So that's either using it, helping us develop it or document it or anything like that. So please do get in touch. And really the ambition here is for this software to become a kind of standard package used in government and beyond for probabilistic record linkage. And of course, that's only possible with the help of people listening in today. So I'll finish up there. I have a couple other slides on future work, but maybe ask me at the end because I realize that I'm 1 minute over now. But thanks very much for listening.
Thank you very much, Robin. Would people have any questions? Robin, there is a question in the chat. What is the language behind it?
Sure. So it's programmed in Python and it uses Apache Spark. So it's actually PySpark. So Spark is where it is executed, but the library is written in Python.
And I think someone had raised a hand. Maybe that was an accident. Oh, yeah. Dr. Griffiths-Rees. Yeah. Would you like to unmute yourself, please?
Hello? Can you hear me?
Yes, yeah, go ahead.
Right. Hello. So first of all, thank you very much for this talk. I am waiting to hear back on a grant applications to do something that has quite a lot of overlap with this, and I'm feeling like a bit of a moron for not knowing about your project until my friend suggested I come to this. So first of all, it's a really fascinating project. The number of applications are considerable. The one and one of the key things I was looking into was applying geographic distance as another metric of similarity, potentially with a distance decay function from between the two records. If you treat one record as the kind of primary and then other as potential matches. The one other thing that we had talked about in our proposal was also using network information. So this was looking at my project currently. One of my projects currently involves matching records of board members across companies and charities. And you can look at that as a network structure. And the extent to which you have name similarity in terms of institutions that they're connected with, and the number of distances within a projection of those networks. And I just wondered if that was something else that had come up in your project.
So I think similar things have. So I won't spend too long on this, but the two things, we should definitely have a chat first of all, because the two things that we provide really, and I think that this is where it's relevant, are two hooks. So where people are doing comparisons between arrays or records, you can inject your own function into that comparison, whatever that may be. So it allows you to choose, like you can be creative about it basically. And then the other thing that we're working on at the moment, and we're actually basically almost done on, is having another hook for graph analysis. So where we're talking about clusters that come out of record linkage, at the moment we just use connected components to resolve that, which is kind of all right, but there's a lot of room for improvement. The other thing that we're working on at the moment is having a hook to allow people to sort of inject their own graph algorithms into the software. So there's basically a lot of scope, sort of using this as sort of the template, injecting your own bits into it to kind of superpower it, if that makes sense.
Thank you to Robin first. That was very interesting and exciting. Extremely flexible and promising. Okay, my name's James Deutsch. I'm from the Intensive Care National Audit and Research Centre, and I've got honorary appointments at LSHTM and UCL. This talks about a chapter that we wrote for the National Statisticians Quality Review with Katie Harron from UCL and Peter Christen from Australia National University. So 15 minutes, the chapter provides an overview of a lot of conceptual theory and practical advice about linkage quality assessment. And 15 minutes isn't a lot to cover all of that. So I'm going to focus on some of the key points and take-home messages. And firstly, there are two different applications of linkage quality assessment. One is effectively as part of the linkage process. So in designing and refining linkage algorithms, working out which algorithm is performing best and to choose between them, and in quality assuring linked data, which pretty much means identifying some of the false links and excluding them from the data, sort of cleaning it, a final step in the linkage process to improve the quality a bit. But what I'm going to focus on more is quality assessment for the purpose of analysis of linked data. And this is what I think we're principally interested in as statisticians. So I ask you a question. As a statistician, which would you prefer? To know that the data have as few errors as possible, or to know the rate and distribution of errors so that you can account for them in your analysis? So currently, almost all of the effort that goes into linkage quality assessment is during the linkage stage. It's quality assuring the data and improving the linkage algorithms, and almost very little sort of time, attention, and effort at all is put into understanding the quality of the data that comes out at the other end. And I think we need to balance that out more, because any statistician I know will say that they'd much rather understand how good their data are than not know how good it is, but just have some assurance that, oh, it's as good as it can be. But it's part of the reason that we don't have much information about quality of linked data is that it's really hard to do, as I'll show shortly. So one of the reasons it's hard is that uncertainty is implicit in data linkage. There's no escaping it, really. It's similar to missing data. We're starting from a position of the unknown. We don't know how these files are meant to come together or how they're meant to be duplicated, and we're trying to reduce that uncertainty, trying to make reasonable assumptions and analysis in the face of the unknown, in the face of the uncertainty. And there's going to be unknown unknowns that we can't do anything about. Just like we can't test the validity or plausibility of the missing at random assumption. The same thing applies to linkage error. What I mean is sort of illustrated if we imagine a spectrum of all the possible candidate links, all the pairs of records that we're considering for linkage. Well, the true matches are going to cluster up one end of the spectrum. They're going to generally have high levels of agreement and low levels of disagreement. The non-matches are going to be clustered down the other end of the spectrum with high levels of disagreement. But one important thing to note here is that the size of these curves is not at all to scale. So in nearly any linkage application, the number of non-matches for every true match is several orders of magnitude out. So there might be 1 million or 100 million non-matches for every one true match. And so you can imagine how the tiniest little tail of of this big bump on the left-hand side can easily sort of swamp the tiny little bump of matches on the right-hand side. But the problem of linkage can be thought of as dividing these record pairs into three groups. We've got those that we're really confident are matches, and we can just treat them as definite matches. Then there'll be a whole lot of others that we're quite confident are definitely not matches, and we'll classify them as not matches. But in between, there's nearly always some residual degree of region of uncertainty where these curves overlap. And for a given pattern of agreement, some of the record pairs will be matches and some of them won't be matches. How big that region of overlap is on the quality of the data. If you've got error-free unique identifiers, then in a sense the data are already linked. That's not really linkage. That's just a lookup table. That's just restructuring the data. Linkage is the process of finding those links when it's uncertain, when we don't have unique error-free identifiers. And an implication of this is that linkage error is generally unavoidable. We can have a really precise algorithm that doesn't include any of those possible matches, and all of the links that it does return will be high confidence links that we're certain really are links. But there will be some degree of missed links, which is a type of linkage error. Or we can go for a more sensitive algorithm that includes some or all of those possible matches that will have a high degree of sensitivity or recall, but a low degree of precision. Some of the links are going to be wrong. Next key point, which we're going to come back, which I'm going to get into more detail about soon, is that just as sort of is that the quality of linkage is generally unknowable. There are only indirect or partial assessments are possible. It's generally, because we're starting from that position of unknown, it's generally not possible to get rid of all of the unknown unknowns. And I'll briefly go over some of the techniques that are available and show how they're angles to get us some information about the rates of linkage error or the distribution of error, but none of them are going to give us all of the information that we really want. And the third thing to be really cognizant of is that there are multiple dimensions of linkage quality. So we've already introduced the notions of sensitivity and precision, or recall and precision in linkage, and missed links and false links, and how there's generally a trade-off between these. But there's a third dimension that is important too, which is kind of a combination of these. So these four examples that I'm showing up the top, the one on the left is the truth, right? Then we've got three different linkage algorithms on the right-hand side. Each of those linkage algorithms has exactly the same match rate, exactly the same precision, exactly the same recall, the same number of missed links, the same number of false links, but they're all completely different in terms of how you would analyze that data. Each of the clusters, whether it's 2 or 3 or 1 dot here, is you can think of that as being a person or an entity, whatever it is that you're trying to link. Right? And these three different clustering outputs have different implications for analysis of data, even though they all have the same error rates. So we need to understand the precision, we need to understand the sensitivity, and we need to understand the impacts of those two on clustering if we're going to be able to make plausible assumptions in our analysis of linked data. And the right balance between those three depends on the application. In some analyses of linked data, missed links will lead to missing data. In other analyses, they'll lead to misclassification or measurement error. In other analyses still, they'll lead to erroneous inclusion or exclusion from an analysis and the selection bias that can introduce. And in some analyses, missed links can lead to clustering errors, which might be one person's record being counted as if it were two people. And that will often involve some degree of error or misclassification as well. So instead of one person who was admitted to hospital twice, it'll be two people who are admitted once. False links, similarly, in some cases will lead to misclassification and measurement error. In others, they'll lead to selection bias, and in others, they'll result in multiple people's records being counted as if they only related to one person. So what can statisticians do about linkage error? Well, we can do sensitivity analysis, but to do that, where we sort of vary the linkage algorithm and see how the results are affected. But to do that, we need information about those. We need those uncertain links. We need access to them, and we need information about how much confidence we've got in the link. Ideally, a match probability, but those can be very problematic to estimate validly. And the thing to note about this is with that trade-off between sensitivity and precision and the implications for clustering, it may be that none of the linkage algorithms are going to be error-free. And there's no guarantee that just by changing the linkage algorithm, you're actually even encompassing the true unbiased parameter that you're trying to estimate. So I'm generally not a big advocate of that. I think the future lies in probabilistic analysis, imputation-based approaches to linked data, and bias analysis, where we work out what are going to be the implications of linkage error for this analysis, and then try to estimate and make plausible assumptions about the rates and distribution of error, hopefully informed by linkage quality assessment, and adjust our analyses accordingly. So the paper, I'm not going to go into these in detail in here because there are a number of them on the next slide too. Different techniques, ways of getting some information about either the rate of missed links, the distribution of missed links, the rate of false links, or the distribution of false links. And when we understand the distribution of them, then hopefully we can also sort of understand their implications for merging and splitting. There's clustering errors. But none of these are perfect, except perhaps for applying the linkage algorithm to a gold standard set of training data. But training data is it's a unicorn in linkage. It's essentially mythical. The only way it's ever created is by human decisions being applied to imperfect data. And the human decisions are going to be imperfect. And if the data quality isn't there, then really all we're training algorithms to do, or assessing quality with respect, is to identify records that have sufficient data quality for a human to be sufficiently confident in linking them. And that's not what we want to get at as statisticians, when what we really want to know is the underlying error rates. So there are some techniques that can be applied with access to identifiers. These are techniques that are sometimes used by data linkers, and there's actually a range of techniques that can be employed by analysts without access to identifiers, using de-identified linked data to get some handle on these key error parameters that we need to know. But to apply these techniques, we need access to the right information, and that's why I suggest these as minimum outputs for linkage. So these are things that I think we can do as as data linkers to produce outputs that are more useful for analysts. So this include detailed information about the linkage algorithm, including the approach to data cleaning. Include record level information about matching variable quality. This is one of the lowest hanging fruit, I think. Just indicators of whether each matching variable was present or not, whether it was valid or not. So if records had no, had few or no valid matching variables, then we know they're not going to have been linked. And we can look at the characteristics of those records and learn something about the distribution of linkage error from them. We need to include link level information about match quality, match weights, match probabilities, match ranks, that kind of thing. We need to include the uncertain links wherever possible. And if it's not possible to include those uncertain links, then we should be providing aggregate statistics about them as detailed as we can. And similarly, if we're doing any sort of quality assurance, identifying some false links, it's nearly always only the tip of the iceberg. And those records that were quality assuring and excluding can provide really valuable information about the distribution of false links to analysts. So we should be including those quality assured links or aggregate information about them wherever possible. I'll leave it off here and leave you to read this general advice for data linkers and statisticians and open it to questions if there's still time. I may have gone over already. I'm not sure. How are we doing, Liz?
Thank you very much, James. Do we have any 2 or 3 questions? We're running slightly late, but we can still take 2-3 minutes of questions.
I have a question.
Go ahead.
Okay. Thank you very much, Doctor, for this well presented lecture. In a situation where you are linking data set from one set to another set, you have what I call an identifier in the first set to be able to pick some variables in the second set. Now, can this result into linkage error? And if it does, then how can you minimize it? Welcome again, please.
Sorry, I'm not sure that I understand the question.
Okay, now you have the 2 data sets.
Yes.
And in the first data set, you have a linkage, or what I may call an identifier. Then you have some variables in the second data set that you wish to link into the first data set.
Yes.
Now, when that is done, does it lead to linkage error?
Nearly always.
Then how can we minimize it?
We can minimize it with sophisticated approaches like Robin was presenting before, with using Splink and probabilistic linkage algorithms and machine learning linkage algorithms, which I don't draw a big distinction between those and probabilistic. I think they end up working in very similar ways, but the linkage is a bottomless pit in terms of there's always more that you can do to go a little bit further in minimizing linkage errors and improving linkage algorithms. And it's a similar story for analysts working with linked data, in that there's always a bit further we could go in digging into linkage error and trying to understand linkage error. And ultimately all linkages have to find a balance between the quality of the data that's being fed into them, the needs of the application in terms of how high quality the linkage outputs have to be, and the resources that are available to the data linkers. And analysts statisticians similarly need to find a balance between how good the linkage is to begin with, how many sources of information we have available to us to help understand and assess the quality of that linkage and reflect it in our analysis, and how much time we have to put into our analysis and how much complexity we're prepared to accept. So I don't think there's a straightforward answer. Sorry.
No.
Thank you very much. Thank you. So we now move to the final presentation before the discussion. So after this presentation, which I hope will overview everything, coming from Rachel Shipsey and Josie Plachter from the French Statistics.
Thanks very much for that, James. We've actually got a bit of a problem with reporting our bias that we're hoping that you can help us with. So maybe some questions at the end. But let's get on with the talk. So I'm Rachel Shipsey, and I'm an operational researcher in the data linkage team in methodology at the ONS. And with my colleague Josie Plachter, we're going to be talking about a method that we have developed to link data sets when the personal identifying information, or PII, has been hashed. And we call the method derive and conquer. It actually started off being a divide and conquer method, but in the end, derive and conquer seemed like a more appropriate name. So you probably all know the saying, if life gives you lemons, then make lemonade. And we feel like we're in that situation because we really don't want to be working with hashed data, but that is what we have been given to work with. So rather than saying we can't link that, we wanted to come up with a method that would enable us to link the hash data so that we could at least know how comparable it is to linking to data in the clear with the particular data sets that we were working with. So hash data looks a bit like this. So the analogy is, if data providers insist on hashing their data, then see if you can work with it. And the data sets that we've been working with using this method are the DWP Customer Information System, which we'll refer to as SIS, and the Patient Demographic Service, PDS. And we didn't have access to the SIS data in the clear when we were designing the method. So we also used the 2011 census data as a proxy to develop the methods. We linked that to the PDS to develop the method in the clear. And the linkage variables were hashed using the SHA-256 hashing algorithm, and SHA stands for Secure Hashing Algorithm, and 256 is the number of bits in the output, although we actually work with 64-character hexadecimal strings. Now, there's no decryption algorithm per se for hashing, but it is possible to reverse the hashing by performing a dictionary attack. And that's where you just, say, take a load of names from a dictionary, telephone directory, for example, and you apply the hashing algorithm to them. And then what you've done is created yourself a lookup from plain text name, i.e. Rachel Shipsey, hash that, get the string that looks a bit like this. So to prevent that type of attack happening, we use a secret key, which is called a salt, which is just another random 256-bit string that is appended to the values before they are hashed. And that prevents a dictionary attack because the attacker would have to know the value of the salt in order to create that lookup. So that's just a bit about what we've done and why. And I'm going to hand over to Josie now, who's going to tell you a bit more about the actual algorithm.
Thank you, Rachel. So a very whirlwind overview of the technicalities of derive and conquer. So derive and conquer is a specialist deterministic or rule-based linkage algorithm. It's designed to work with very large hashed data sets. And even before linkage begins, there is a huge amount of work that needs to be done before we can even think about starting. And this initiates with some cleaning and standardization. And even this is not a trivial task. So for this project, we are collaborating both within multiple ONS divisions and also with multiple government departments. And everyone has to agree a protocol and standardization and then stick to it. As an example, here are the standardization rules for how we deal with names. And you will notice 6 and 7 mention some hyphens, and just agreeing what we were supposed to do with hyphens in forenames and surnames was a conversational debate between multiple teams and organisations. And Rachel remembers that it was known as hyphen gate. And that's just names. So similar rules have to be agreed for all of our variables. And once these have been agreed, they need to be tested because we need to ensure that each department's code is in harmony. So ensuring that for a given input, we are all producing identical outputs. Otherwise, the hash of them will not link. We need exact agreement on hash. So next, before we hash the data, we attempt to capture similarity before hashing. So this is done by creating 57 derived variables. These capture substrings and patterns of our raw variables, and we can then link on these. And again, these derivations must be agreed and tested between the departments to ensure that they are in harmony. These derived variables include things like first part of first name, second part of first name, soundex of first name, double metaphone of first name, first 4 characters of first name, last 4 characters of first name, nickname of first name, etc. 57 variables later. In total, there are 18 first name variables alone. So the idea here is that any error in the full name variable will cause the hashed value not to link. But if the derived variables link, this can represent partial agreement. So to establish which 57 derived variables gave us the most value, so found the most matches without creating false positives, we used 2 proxy data sets. So we used the 2011 census and we used a historic version of PDS called PR. We used these because we had access to them in the clear, so unhashed, and they are England and Wales data sets. It should be noted that we did receive a sample of in the clear records from DWP after the linkage. And it wasn't until we received this that we had any idea how these 57 derived variables worked on the actual SIS to PDS linkage. They'd only ever been tested on census and PR. So next, we then have the hashing. So hashing is relatively straightforward, but it is complicated by the use of the salts, which Rachel introduced. So these salts have to be shared securely between the parties. They have to be stored securely, and only certain people are allowed to have access to them. For the implementation of derive and conquer, we also had to get DWP and HMRC to agree to use the same salts for some groups of variables so that we could compare across variables. So for example, first name and middle name to check for transpositions. So when someone has accidentally written their first name in the surname variable, for example. So finally, we are onto the linkage itself. So derive and conquer, I mentioned, is a deterministic method. However, because our derived agreement status is calculated dynamically between pairs, it is necessary for us to use the blocking methods that are similar to those seen in probabilistic methods. So we use 10 loose blocking passes to group together potential matches. So for example, any PDS and SIS record that agree on postcode and date of birth. We then take our blocked pairs and we generate a derived agreement status of each of their raw variables. So for example, for the raw variable first name, we see if any of the first name derived variables match between the pairs. We then classify the agreement as exact, strong, weak, transposed, no agreement found, or there is a missing value. So if we take an example, if the soundex or nicknames match exactly, we would classify the pair as having strong agreement for that name. This is then done similarly for the other names, so middle name and surname, date of birth and geography. Research was carried out on our proxy data sets that we had in the clear to determine which of our derived variables constituted an exact, strong, weak, transposed, etc. match. We then run match keys that are slightly different from the traditional match keys that you might be familiar with. So they run on derived agreement status instead of a specific variable. So for example, we might have match key 8 and say any blocked pair that matches exactly on first name has strong agreement on surname, exact date of birth and exact geography would be declared a link. For match key 28, we might have strong first name, strong agreement on middle name, exact date of birth, exact geography, and exact sex. There are 45 match keys in total in the derive and conquer algorithm, and they are numbered in hierarchical order, with match key 1 being the strictest. So we also have a few slightly more novel match keys that we use. So we use associative matching, and this makes use of relationships between multi-household persons who have moved house. So if we can see that more than one person is associated with two different addresses, we can imply that this is a moved household, and we can make the person link despite different geography. We also use unique biography to make a link without geography. So if there is only of someone with Napoleon, Leonardo, something or other, because it's very, very unique and we've got full coverage data sets, we make that link. However, this kind of technique should not be applied to smaller data sets, as unique biography would not be meaningful. We then look for duplicate matches found on exact match keys. We assume that these are caused by duplicate records and retain them. Duplicate match keys that are found on non-exact match keys are discarded. If non-unique matches are found on different match keys, then the strictest match is kept and the others are discarded. And so this produces a result in the form of a list of matched pairs and two lists of residuals, so one from each data set. Before we move on to the QA step, this diagram here represents how the algorithm runs on big data. So we are talking data sets with hundreds of millions of row, which would take ages to process pair by pair. So instead, we use distributed computer system, so the PySpark, which Robin also talked about, and this dynamically takes our code and runs as much of it as it can in parallel. So blocking is the slowest part because all of our records have to be available to every block. But when we derive our agreement and calculate the match status, all of this can be done in parallel. This system can also process the pairs themselves at the same time. So we now need to check how well our method is working with the sys data. So DWP agreed to supply us with samples of data in the clear. So these comprise of 2,000 matched records from each match key and a random sample of 600,000 residual records. So these are sys records that have not been matched. We conducted a clerical review of our matched records to estimate a false positive rate. And we used a probabilistic matching exercise using and matched it to the entire PDS data set to estimate the false negative rate. We also wish to attempt some form of bias analysis. However, we are still thinking about the best approach for this. Once we've worked this out, we will be asking DWP to carry out a similar bias analysis of the linked and unlinked sys records. We can't do that bit because we obviously don't have sys, or we do, but it's all hashed and useless. So accuracy first. So we matched 64 million records. This is about 85% of the PDS records and 59% of the total sys records. From our clerical review, we estimated that we have around 3 million missed matches and only around 37,000 of the matches we made were incorrect. So our precision and recall are pretty high considering that this was automatic matching. Even when we calculate confidence intervals and take the 95%, the precision is very high. The traditional and seeing how evenly they are distributed across the population. So if errors are clustered in a particular group of interest, so for example, a specific ethnic group or a specific age group, this can adversely affect any statistics that are produced from the linked dataset if those variables are used from the analysis. So our problem is because we only really have a relatively small sample of records in the clear from DWP. So we only have a very small number of records that we can examine in the clear. And it does not really give us enough of an indication of error distribution to report bias. So what I'm presenting on this slide is the information that we do have. So this graph looks at the whole of PDS and it classifies each of the PDS records by the ONS's hard to count index. So this index was built to classify geographic areas using characteristics such as ethnic composition and income to rank how likely they are to be included in ONS surveys. On the x-axis, we have the hard to count rank, with rank 1 on the left being records from the easiest group and rank 5 on the right being the hardest. The furthermost group to the right represents those with invalid geographic information, making hard to count attachment impossible. On our y-axis, we have the percentage of records, and then in blue, this represents the linked records, and the yellow represents those we did not match. So we can see that a higher percentage of easy to count records were linked than hard to count. However, what we don't know is how many of these missed links are errors and which are true non-matches. So, for example, it could just be that hard to count rank 5 records are truthfully not included in SIS, in which case we are correct not to link them. So what we want to know is how we can estimate which of these yellow records are mismatches and whether the distributions of these errors is even between groups or clustered in a particular group. So what we've tried to do so far is narrow down where our errors are. We're considering removing anyone with invalid ages and anyone with invalid geography. But particularly this invalid geography is very difficult because people generally who do exist and do exist on SIS may put an incorrect geography out of it, a typo, or they just misspoke. So even that, if we excluded everyone with an invalid geography, we would end up probably excluding our errors as well as the true missed matches. We welcome any advice that our audience may have here. So I'm now going to pass back to Rachel, who will discuss some of the limitations of this method and our recommendations.
Thank you, Josie. So first of all, I'd like to talk about some limitations of this specific method. So first of all, quality. So our clerical review showed that derive and conquer did work very well on SIS and PDS, and they were the data sets that it was designed for. However, it works less well on census data. And when we tried it out on self-assessment data, the match rate was really low, about 35%. So this method just cannot be just used out of the box on a variety of different data sets. It would have to be designed bespoke each time for different data sets. Another problem is that some of the variables that are hashed don't contain a lot of different, a lack of entropy, and this could lead to an attacker associating together, for example, a common name with its salted hashed value. Now, personally, I don't think this is a cause for concern, because if you know the hash value of Smith, that doesn't help you to find the salt or any other values associated with Smith or any of the other names. If it is really a concern that common names could be identified, then it is possible to disguise them by adding lots of fake records into the dataset, but I don't see the need for that personally. Now, another limitation is, as Josie's explained, the method runs on a distributed computing platform that we're very fortunate to have at the ONS, and this allows us to make billions of comparisons in a timely manner, but obviously not all organisations will have access to such a platform. And some more general limitations of linking with hashed data. So the amount of collaboration that was required was intense. All the parties involved have to work together very, very closely. And that was true all the way through the process, from agreeing the standardization, the cleaning, the derived variables, the salts, etc., to doing the QA work, which is more than just providing samples, but will also involve analysis by the supplier. Josie's mentioned hyphen gate, and just agreeing how to standardize names took a long time, you would not believe. We did resolve it in the end. And the time needed, it takes much, much longer to develop the method because you can't easily see the effects of changes that you make. So normally when you're designing a linkage method, you would try something, you would have a look at what it's doing, you might make a tweak, then you'd have a look at what that tweak, the effect of that was. But when the data is hashed, you just can't do that. And that we found really frustrating. It just takes a very long time. And we work with proxy data sets to sort of get around this, but that's not ideal because, as I've said, you need to design really bespoke for the data sets that you're dealing with each time. You might think that because the data is hashed, there's less need for security, so we're saving something there, but actually that's totally not true. There's been no reduction in security processes just because the data is hashed, so there's been no savings in terms of cost or time. And in fact, setting up different project spaces where one has access to hash variables and another has access to in the clear variables, etc., that all takes extra administrative and logistic time and effort. So there was absolutely no savings there, probably the opposite. And I'd say that using hash data is more expensive because of the exacting quality requirements for the cleaning, the standardization, because of all the collaboration that is required and the extra time that is spent. And the data supplier must agree to provide some data in the clear, because otherwise it is not possible to carry out any quality assurance. And in that case, we think that the linkage just should not be used, certainly not to produce official statistics. So the flip side of this, the benefits of matching in the clear. First of all, clerical review is possible. So whilst you're iteratively developing the method, and also to review difficult cases during the matching, and none of that is possible with the hash data. And there's less work because when you're matching in the clear, you still need to carry out all of the standardization and cleaning processes. Obviously, you need to do all of that, but it's much easier because one team can clean both data sets. So they can use the same methods, they can use the same platform, and they can tailor the cleaning to the particular data sets. And the data supplier only has to hand over the data. They don't need to get their hands nearly so dirty. And actually working on different platforms did cause us a bit of a problem. So for example, the double metaphone string comparator gave different results from our implementation of it to the DWP implementation of it to the HMRC implementation of it, and that all took quite a lot of time to sort out. And there's no point hashing something unless you know that it was the same before you start off, because it's not going to match hashed otherwise. So although I'm really up for collaboration, and as Robin mentioned, we worked with him a little bit on the Splink stuff, and that was fantastic. I really enjoyed doing that, and I would like to see more of it. But the very, very close sort of nitty-gritty collaboration that was necessary to get Derive and Conquer to work was quite challenging at times. We were all in different locations, different processes, different sets of people, have to sign everything off. It did take a very long time to get sorted. So I'd say that matching in the clear is quicker, it's cheaper. You don't need to wait for samples in the clear so that you can do your QA. And I would also say that for some data sets, there's just very little alternative to linking it in the clear. Using the hash variable simply won't give good enough results. And there's not much point going through all this time-consuming and costly exercise to link using hash data if the results cannot then be used to produce high-quality analysis and statistics. So I've already mentioned the SA linkage, so we tried to use Derive and Conquer on that, but the match rate and the quality was just too poor to make that usable at all. So I'm in a really weird position because I'm really proud of this method that we've developed. It's a great method, it works really well, but I don't really want anyone to use it because I would much rather that they have access to data in the clear, and I think that's what we should be pursuing. However, if we do have to work with hash data, then we believe that Derive and Conquer method could be used in some circumstances to get an acceptable accuracy in terms of the false positives and false negatives. But if departments are going to go ahead with linking hash data, then they do have to be prepared to throw a lot of money and time at it, because it will take a lot of time and money basically to get a decent result. Further work on this is that we'd like to carry out a very thorough and fair, properly resourced comparison of data linkage using in the clear versus using hash data, because although comparisons have been done up to now, they have been rushed due to time constraints, and we don't think that all the implications of using hash data are properly understood as yet. So there we are, we have some lemonade. I'll be taking any questions if someone would like to ask any, or I could ask some of James if that would be okay.
Thank you very much, Rachel and Josie. We've got two options here. We can move on to the discussion where I suppose people can ask questions, or we can take some questions. The discussion is led by Dr. James Tucker from ONS. So, James, what do you think we should do?
Hi, so I'm filling in for James, who couldn't make it. It's from Data Quality Hub, which is James's team. What we could do is maybe just move on to the discussion section, which would be sourcing any questions the audience have for any of our presenters that we've had today, but also any questions you'd like to put to each presenter. So that's how I was going to run it anyway. So you've got kind of two options here. You could post questions in the chat window, but also if anyone wants to ask a question to any of our presenters out loud, you could raise your hand now, and I can go through and invite you to ask your question. Okay, so first up we've got Ken Humphreys to ask a question.
Okay, so I work at National Records of Scotland. It's doing data linkage, and we use a bit of open source software. They're called Link, so not it's called Big Match. And one of the problems is you can't get all of the candidate pairs, so you have to set a threshold. That means that your information on missing links is limited. Any advice around handling that?
I do.
Hello?
I'm not sure who the question was directed at, but I do have
go on, James, you'd probably be good. Yeah.
So in those situations, what I think is important is to have, wherever possible, multiple thresholds. So you might have a threshold above which you're prepared to accept links as being definite matches, but ideally you'd also have a lower threshold that pulls in those uncertain links, and so you're not only working with one threshold and only returning the definite links. You don't need to have all of the candidate links back, because that's usually that's often too big a number to even create the data set with. What all you need is the ones at the high end of the spectrum, just below the threshold, if you like, where you're willing to accept them.
Okay, and that just gives you an idea of how many you're likely to have missed.
No, it unfortunately doesn't give you that, but you can look at those records and think, okay, these records are probably a mix of true non-matches and missed matches, and we can look at what sort of records, what the characteristics of those records are, and from those make some inferences about the likely distribution of missed matches. And we can also implement sensitivity analyses. So we can do our analysis using just the higher threshold, and we can do other analyses using lower thresholds down just through that range of uncertainty. So by providing those records, those uncertain records near the threshold, it opens up some possibilities for analysts to do a bit more about linkage error.
Okay, that's helpful. Thank you.
Okay, brilliant. Thank you. We've had a question in the chat window for Rachel. So it's from Annabelle Summerfield. Why do you think this method was less effective on other data? Do you know which bits let it down but worked well on the data you had tested it on?
Well, hi Anna, thanks for your question. So I think it doesn't work so well on census data just because of the messiness of the census data, all the scanning errors and things that we have to deal with there. You just can't capture everything in this set of derived variables. It wasn't actually me that did the self-assessment linkage, but I think that must come down to the quality of the variables. I don't know if Josie can.
Yeah, so self-assessment is incredibly messy. I think some of the highlight error issues are that the wrong thing is often written in the wrong box. So for example, you might have a name field. So this is where the person is supposed to write their personal name. So I'd write Josie Plachta. A lot of the time you end up with a company name in there. And without incredibly bespoke cleaning. So for example, you might have John Smith and Sons. Like you would have to have incredibly targeted cleaning to capture the fact that that's a company name. And without being able to see the data in the clear, you can't then tweak your cleaning and standardization code to do that. There is a lot of missingness in self-assessment data. There is also a lot of associated variables. So the second probably highlight of the self-assessment data is that you have about 4 different address fields. And so the one which is supposed to represent personal address, there are something like 10,000 taxi drivers in London, and all of them have exactly the same personal address. And it should be their home address. That's what they should have written there, but they haven't written it. Instead, they have all written this one company that does tax records for taxi drivers in London. So you end up with not particularly like sort of distinguishing variables in self-assessment. So it's an issue of incorrect things being written in that cleaning methods cannot account for. There is a lack of distinguishability in its variables, and there is a lot of missingness. Anything else, Rachel?
That was a beautiful summary. Thank you very much, Daisy.
Since Robin's the only one who hasn't answered a question yet, I might go back to a couple of the questions that you weren't able to answer earlier, Robin, if that's okay. So there's a question earlier that we had for you, Robin, on how would Splink deal with addresses which could be written in English or Welsh?
Yeah, so what we do in Splink is we provide a bunch of ways of comparing data which are really common. So comparing things like people's names, dates of birth, maybe geographical stuff. This probably falls a little bit outside what everyone wants, and so it's sort of up to the user to be a bit creative about how you sort of pre-clean your data and perform record comparisons. So what Splink allows you to do is sort of define how you want the record comparison to occur yourself using SQL. So in this kind of case, what you might do is you might even have two address columns, one for the English and one for the Welsh, where you null out the address if it doesn't exist. So Splink explicitly deals with nulls correctly. So basically, you don't need to worry about having nulls in your data set. That would be quite a simple version. You can get quite sophisticated, and you could set up rules like, I don't know, if the postcode exists, do one thing, because presumably that's like language agnostic. Or if the postcode doesn't exist, then do something else, or maybe like put the various addresses in arrays and find all pairwise comparisons in those arrays. It's kind of up to you, but you should be able to get, I would have thought, quite a good result by being a little creative.
Brilliant, thanks very much. And one other question for you, Robin, that came in was on how much data cleaning is required.
Yeah, so I think this is just something you have to do with you have to do whenever you're doing record linkage, right? So the more effort you put into data cleaning, the better your result will be. So for instance, you're going to want to look at people's names and try and standardize that in some way. We provide a few functions for doing that, so like splitting the name across fields. But there's I think there's a lot of creativity in the data cleaning step, and it's quite dependent on the data you have. So we don't want to be like really opinionated on how you want to do this. So it's like up to the user to think, well, how can I make the data like as common or standardized as possible? So we've got a library of standardization functions for the most common cases like names. But other than that, like it's kind of up to people to decide the best way to clean their data to put it into the matching problem. But that's like not the kind of core problem we're trying to solve. We're trying to say, once you've cleaned your data, how can you quickly and efficiently do probabilistic linkage on really big data sets?
Yeah, it's part of the balancing act that is that's inescapable, and it's also worth acknowledging that that balancing act needs to be taken in the context of the quality of the data. So more standardization is not always a good thing. Data cleaning, correcting known errors, that's usually a good thing, but even that's not always a good thing if the data generating mechanisms are the same across the data sets and the errors are likely to exist in both data sets, then you wouldn't actually want to clean them. And similarly, a lot of standardization is actually throwing out information that's in the data. So, you might have 3 different spellings of the same name. If they're if the data quality is low, then they may be all the same person, and it's just spelling errors, and standardizing them is a good thing. But if you're working with really high quality data, then those are much more likely to be 3 true different spellings of the same name in 3 different people. And so data linkage is an art. It's not a science, and it takes access to the identifiers, it takes experience and knowledge of, it takes knowledge of the data set that you acquire over time, the specific data sets. It takes experience with linkage in general. And these are things that are ultimately only going to be acquired or be best acquired by having authorities, linkage units dedicated to doing this work day in, day out. And currently, we don't have many people doing linkage work, as their bread and butter. It's something that most of us do part of our time to support ad hoc projects. And I think one of the things that this country needs most is investment in dedicated linkage infrastructure.
Brilliant. Thanks very much, both. Rachel, you've got your hand raised. Did you have a question or something you wanted to raise?
I have got a question, probably aimed at James, but anyone else can chip in if you've got a good solution to it. So Josie alluded to this bias problem that we have. So we've got all these unlinked records, and mixed up in them is the true negatives, the records that should not link, and the false negatives, the ones that should link, but we haven't managed to. And our clerical review suggests that there's about 4% linkage error, things that we should have linked that we haven't, but then there's like another 14% on top of that. So how can we possibly split the ones that should have linked but haven't from the ones that shouldn't have linked and haven't in order to report the bias? Because at the moment, all we can do is report the bias comparing the linked with the unlinked, or the linked with the whole data set. And that doesn't seem right to us, but we can't think of any other way to do it.
The short answer is you can't.
Okay.
The better answer is that there are a few different ways that you can get some information about that. So we can look at the records that have terrible quality matching variables. We can see if most of the matching variables are missing, or the key matching variables are missing or invalid. And so we can identify some, it's usually possible to identify some subset of records that are unlinkable given how the linkage was done, given the linkage algorithm that was used, right? Yeah. And those ones are missed links. It doesn't tell you how many missed links there are in total.
It doesn't necessarily though, does it? There might be genuine false negatives that have just got terrible matching variables.
Well, those records are going to have been unlinkable, and if you're expecting them to link, then you'll know that they're false links.
Okay.
And so this is another. This gets into another technique that is a way that we can get some information about missed matches, and so this is using positive controls. So sometimes there's a whole data set, sometimes there's a subset of a data set that, because of the information in the records, you believe ought to link. These are records where you're expecting 100% match rate, and if you look at those records that don't link, then those are definitely missed links. But again, they're not going to give you information about the number of missed links, the rate of missed links, unless it's the whole data set that you're expecting not to link. But unless it's the whole data set you're expecting not to link. But even then, it doesn't necessarily give you the rates of missed links, because some of the links that you're making might be wrong, and those can actually represent false links as well. Those false links can have missed links associated with them. Yeah. So it's complex. We cannot measure linkage error perfectly, right?
No.
There's a set of techniques that we can use to get some information about it. We can and we need to do all that we can with the resources available to us as data linkers, and we need to accept that as data linkers we can't do everything, and some of the techniques even are may only be able to be implemented by the analysts who get the clinical data that sometimes, you know, data linkers, if they're acting as a trusted third party, never even have access to that data, and that can include some information that helps to get angles on linkage error. But you can't report the bias. You can only provide information towards understanding the bias.
Okay, that's helpful. Thank you. We could think about that positive controls thing, but if we were to request a sample of people we knew that would link, that might start people getting twitchy, because then we're requesting particular types of people. So I can see a problem with that as well. So it is a really difficult problem. I'm a bit reassured that you've said that it's hard, because we have been struggling with it for a while now.
This is why I'm so opposed to tying data linkers' hands with privacy preserving linkage methods and hashing and all the rest. What we need is data linkers to have the best resources available, you know, access to the information they need to do their job as well as they can, and we need the systems to control access to that identifiable data, that sensitive data, that don't involve tying data linkers' hands, and ultimately reducing the quality of the linkage and distorting the analyses of the linked data.
Yeah, thank you very much.
Okay, thanks very much, everyone. We've run out of time. I noticed there's a couple of questions that we didn't have time to answer. What we might be able to do is perhaps provide a written response to those questions from the presenters and send it out after the webinar. So all that's left to say really is, I hope you enjoyed today's webinar. Thanks again to all of the presenters. I am going to just post a link to the Joined Up Data in Government Future of Data Linking Methods review for further info, because all of the presenters you've heard today have a detailed article in that review with further information on their talks. So do have a look at that if you're interested. So yeah, I think that concludes the webinar, and thanks again to the presenters and for you for attending.